Hello, everyone. Today we're going to talk about a technical interview question that I came across recently, and I thought it was very interesting. So the question itself is very simple. Given a head pointer to a linked list, print its elements in reverse order. So for example, if we're given a linked list of, let's say, three nodes and a head pointer, and let's say its node values are 3, 1, and 2, then output should be 2, 1, and 3. So uh, I guess like the trivial solution to this problem would be using a stack and uh, start from the head pointer, and then we traverse through the list and pushing the node values into the stack as we do that. So it will be 3 first, and then 1, and then 2. And then after traversing, we simply pop all the elements out from the stack until it's empty. So uh, 2 will be popped out first, and we print that, 1, and then 3 after. So this would be O of n time and O of n space complexity, because O of n time comes from traversing the length of n linked list and also popping n elements out from the stack. And O of n space comes from the stack holding n elements. Now, we can improve the space complexity to O of root n, and which is better, and I'll show you how we can do that. Okay, so let's say we're given a linked list of 6 nodes, and then let's say its values are 1, 2, 3, 4, 5 for the simplicity's sake. So the output should be 6, 5, 4, 3, 2, 1. So we have a head pointer, but if we had another pointer in the middle of the linked list, say I call it P, then what we can actually do is we can start from P and push 4, 5, 6 into the stack, and then print them out first, and then move on to the head pointer and push 1, 2, 3 into the stack, and then print them after. So to visualize this, we start from P and push 4, 5, 6 into the stack, and output 5, 6, 5, 4 as we pop them out, and then go to the head pointer and push 1, 2, and 3 into it, and then pop them to print out 3, 2, and 1 in this order. So in this case, we only had 3 elements in the stack, and we only had 2 pointers. So in the stack, we basically, so with 2 pointers, what is possible to do is we can only have n over 2 elements in the stack at a cost of storing 2 pointers. So to give you a better idea, let's try 3 pointers. So I'll call them P1 and P2. So here, what we can do is we can start from P2 and push in 5 and 6. Oops, I'll use the same color just for consistency. Push in 5 and 6, pop them out. So we print 6, 5. Go to P1 and push in 3 and 4, pop 4 and 3, print them out. and then finally move to the head and push in 1, whoops, 1 and 2, and then pop them out and print out 2 and 1. Okay, so in this case, we only had n over 3 elements in the stack at a cost of having to store 3 pointers. So what is the optimal number of pointers to minimize the space complexity? So here we have number of elements in the stack plus number of pointers that are distributed along the linked list. So if we say that the number of pointers is p, then the number of elements in the stack is n over p. So what is the optimal number of p? Because, well, n is constant, it is given by the linked list size. So what we can do is we can actually differentiate this quantity. So we can differentiate it by p to find the value of p that minimizes this equation. So this differentiation should equal to 0 because we're trying to find a minima, and this equals to n over p squared, and of course minus at the front, and plus 1. So we can solve this as p squared equals n. Then we have p equals root n. So we just mathematically showed that the optimal number of pointers is root n, and of course this leads to space complexity of root n because n over root n is root n, so number of elements in the stack is root n, and number of pointers is root n, and we have 2 root n, so the space complexity after dropping the constant 2, then it will be over then. Okay, so how does our algorithm work? We first need to find the length of the linked list, and this gives us number n. And then we traverse through the linked list again, but this time we store a pointer to every root nth node. So if we had 4 nodes in the linked list, for example, then of course we save the first one, but then we save a pointer to a node 2 nodes after that. So this one, because root 4 is equal to 2, so every 2 nodes we store a pointer. So let's say this is P1 and P2. So lastly, what we do is we reverse iterate the stored pointers. So in this case, in the above example, it's P1 and P2. So, and then we reverse iterate it. So we start from P2. And then we push into the stack root n nodes, values starting from each of the pointers. So from the above example, we start from P2, and we push in root n nodes, so that's 2 nodes in this case. So we push this guy in, whoops, sorry. We push this guy in, and then we push this guy in, and then we have a step B in step 3. We pop these 2 push nodes from the stack and print them. And then after that, we go back to step A and then do the same thing with P1. So this gives us O of root n space because we have root n elements in the stack plus root n pointers. Now we have O of n time, and if you're wondering why exactly this is the case, it is because of step 3. So step 3 here, we have a root n pointers. And for every root n pointer, what we're doing is we're pushing root n elements into the stack. And then we're popping them. And this is another root n operation. So since we're doing root n pop, push and pop operation for every root n pointer, that results in root n times root n, and this gives us n operations in total. Oh, and also we iterated through the linked list of length n from step 1 and 2. So yeah, that's also full of n time. So yeah, I hope this video explanation was helpful. If you have any questions, put them in the comment below. I'll explain them as much as I can. And yeah, thanks for watching.